Well, there's some good pointers here, some good advice. Make sure that you guys are taking care of yourselves, both physically and emotionally. We've been in isolation for quite a while. I know I feel like it's really starting to take a toll on me. In fact, I'm going to be attending a online webinar on mental health during this time, and there's a lot of stuff out there. So please make sure that you are taking care of yourself and seeking help if you need it. So we're continuing on with combinations today. What will be new in today's work is we're going to be looking at questions that involve the phrase at least or at most. And what it does is it really just means we're doing questions that have multiple scenarios. So if we're doing a question that says you have to have at most 5 females, well, that means you can't have any more than 5, but you could have less than 5. So you'd have to look at, well, how about having 0 females, or 1 female, or 2, or 3, or 4, or 5. That would be for at most 5. So today is really about figuring out all the possible scenarios that could happen. So our first example, the student council decides to form a subcommittee of 5 council members to look at how funds raised should be spent on the students of the school. There are a total of 11 student council members. There are 5 males and 6 females. How many different ways can the 5-member subcommittee be chosen if there are no restrictions on the number of males or females? So that one is kind of like yesterday's work. You can go ahead, please, and give that one a try. So with no restrictions at all, let's see what we have, my little diagram that I like to make. Here is who is available. We've got 5 males and we've got 6 females that are on student council. And from this group of people, we want to pull out 5 people to make a subcommittee. So there's kind of our general plan in this question. So this little sketch applies to all of the questions A, B, and C. All right, so no restrictions at all. We don't care who is on the committee. We don't care about gender. We're going to say there's 11 people available and we want to choose 5. So with no restrictions at all, 462 different groups or subcommittees could be made. And then in B, exactly 3 females. Now, remember, we are still making a subcommittee with 5 people. So exactly 3 females. So we're going to have 3 females. Here's our planning step where we're just thinking about what are we putting together? What are all the pieces we're putting together to make this subcommittee? So if we're using 3 females, it would be 3 females and 2 males. So that's who we're putting together in this group. So we'll have one combination for the females. So there are 6 females available, and we want to choose 3. And means multiply. To get 2 males, there are 5 males available, and we want to choose 3. Our trusty calculator tells us that there are 200 different subcommittees possible that have exactly 3 females. And then C, here's where we're getting into our new concept, at least 3 females. So at least 3 means 3 or more. So here's where we've got to work with all the different scenarios. So in my planning step, I'm thinking about all the possible scenarios. So I'm going to start off by saying we could have 3 females. And maybe don't write this down right away. I'm just going to kind of space it out the way that I'm thinking through it. Or you could have 4 females. Or you could have 5 females. So that's what it means when it says at least 3 females. Our committee will have 3 females or 4 females or 5 females. But remember that we're making groups of 5. So in this scenario where I've got 3 females, I would also have 2 males. Or here's another scenario. 4 females and I'd need 1 male to make it a group of 5, or 5 females, and this one you don't even really have to write in, but just to make sure all our pieces are lined up, 0 males. So you can hit pause now and go ahead and write that down. Think about what it means as you are writing it. And then for each one of these little subsets of people, we're going to need to have a combination. So let's look at 3 females. There are 6 females available, and we're going to choose 3. And means multiply. So let's look at getting these 2 males. 5 males available, and we want to choose 2. And then remember that or means add. Okay, our other scenario. So 4 females, there are 6 available, and we're going to choose 4. Multiply for the males, there are 5 males available, and we want to choose 1. Or again, that's adding. To get 5 females, it would be 6, choose 5, and we're multiplying by 5, choose 0. Now, kind of like we had the other day, this 5, choose 0, you could put it in your calculator and you'll see that it is just equal to 1. So quite often you won't see this one in your work because you're just taking whatever this number is and you're multiplying by 1, which doesn't change anything. So normally you won't see it there, but remember what I like to do is kind of add up those numbers. If I add up this 6 and 5, that's the 11 people who are available. And if I add up this 5 and 0, that's the 5 people that we are selecting. So it's up to you. You can put that in, or you don't have to put that in. And you can put this into your calculator in pieces, or if you're good with your calculator, you can put it in all in one shot. But do make sure that you pause and practice it. You should get 281 different subcommittees that have at least 3 females. Okay, so we're back to a question with a standard deck of cards. So people who are not familiar with a deck of cards, perhaps you want to have this sheet handy so you can look at it, or maybe on another device, maybe on your phone or on your tablet or something. You've got it open up so that you can see all the cards in the deck. So we have, considering a standard deck of 52 cards, how many different 5-card hands, so making groups of 5, can be formed with no conditions? So please hit pause and go ahead and do this question. This is from yesterday's work. You should be competent with this. So we would say there's 52 cards available, and we are going to choose 5. And that means there are 2,598,960 different groups of 5 or different combinations of 5 cards could be made. And then B, with at least 4 red cards. So at least 4, in our own words, we'd say that's 4 or more. So let's just think about our possible scenarios then. We could have 4 reds, or we could have 5 reds. Because remember, we're only making a 5-card hand, so we're not going to have more than 5. Now, in this scenario where we have 4 reds, we would also have to have 1 black card. And again, that one that's kind of weird, you could leave it exactly as it is right now. If you want to have all your pieces kind of lining up together, you could also say 5 reds and 0 blacks. And then a combination for each one. So maybe at this part of the question, you'd like to hit pause and see if you can finish this one off. Remember that you will need a combination set up for the 4 reds. You'll need another one to get the 1 black, another combination for the 5 reds. And for the 0 blacks, this one is really optional whether you include it or not. All right, so there are 26 red cards in the deck. So to get 4 reds, that would be 26, choose 4, and is multiply. To get the 1 black, there's 26 black cards, and I'm going to choose 1. Or means add. And then to get 5 reds, 26, choose 5. And to get the 0 blacks, this is up to you whether you include this one or not. There's 26 black cards, and I want to choose none of them. Now let me just tell you why I like to do this planning step right here. So before you just jump into this step right here, you should be thinking about the whole plan. And what I like about it is that in this plan, I can set up what I need, the different sets or groups I need, and right below it, translate it into math. So from thinking about just what I need, translating it into math right below. And I think it's important for our connector words too, remembering that and is multiply, or is add, and is multiply. So just that whole right below your plan, you're able to kind of do convert it into math. So again, depending on how good you are with your calculator, you might put the whole thing in all at once. You might put pieces in. I put these first 2 in together, and that was 388,700. And I put these 2 in together, 65,780. Added those up, and my answer was 454,480. Okay, so remember what we're doing there is we're saying there are, in question A, we're saying, here's how many 5-card combinations we could make with no restrictions at all. Here's how many 5-card combinations we can make that have at least 4 red cards. And then our final one here, C, at most 2 kings. So at most 2, you could say no more than 2, you could say 2 or less. So we have to make sure, of course, that we understand what does it mean to have at most 2 kings. So let's look at our scenarios here. 2 or less kings. So I'm going to start with the lowest number of kings that we could have. I think I'm going to need just a little more space here. So the lowest number of kings that we could have, and this one is often forgotten about, we could have 0 kings. Now remember, you might want to wait and write this down at the end and just sort of do the thinking step with me. Or we could have 1 king. Or we could have 2 kings. So 2 or less kings means no more than 2. So there's our scenarios. Now remember the other pieces. If I have 0 kings, really, and I'm still getting a group of 5 cards, what I have is 0 kings and 5 non-kings. Or 1 king and 4 non-kings. Or 2 kings. And the other 3 cards then would be 3 non-kings. All right, let's give this a whirl. So 0 kings. Now again, remember, if you're picking 0 kings, there is only one way to do that. You just don't pick any. So you don't have to include this combination if you don't want to. But there are 4 kings available, and I'm going to choose 0. And means multiply. Now I'm on my 5 non-kings. So again, just for people who aren't familiar with the deck, here's the kings right over here. So if we took away all those kings, all of these other cards are the non-kings. And so 52 subtract 4 means that there are 48 cards in the deck that are not kings. So I'd have to say 48 available, and I want to choose 5. So this is a good place to pause and see if you can finish this question off. Okay, so I'm just translating right from above. So I'm looking at my plan. Now I'm on the or. So for or, I say that's adding. And then I go on to this, how am I going to get the 1 king? That's my next combination right here. So just taking it from my planning step and converting it into math. So to get 1 king, there are 4 kings available, and I'm going to choose 1. And now the 4 non-kings, 48 available, and we want to choose 4. And then to get 2 kings, there's 4 available, and we want to choose 2. And as multiply. To get our 3 non-kings, 48 non-kings are available, and we want to choose 3. So again, this planning step should be really helpful to you. If you just take the time and plan that out, getting these pieces should not be hard at all. So remember, you're just going right from above and you're converting it into math. So when I did my calculator work, I did this chunk, and this chunk. But again, this whole thing could go in your calculator all at once if you're feeling confident about it. It's a lot of buttons to push on your calculator. I have to admit, I'm always nervous that I've hit one of those keystrokes wrong and that something is going to be messed up. I hope that's not the case. we get a final answer, 2,594,400 different hands, different 5-card hands that would have at most 2 kings. All right. You don't have this page in your workbook, obviously, but it's something I want us to take a look at before we try our next couple examples, because it's kind of a common sense thing. And I'm just going to sort of lay out some questions that don't have a ton of details, just so that you can kind of get the idea of it. So there are a total of 123 groups of toy cars that can be made. So that's without any restrictions. So let's say you've got all your little Hot Wheels cars out there and you're making as many different combinations as you can. And there's 123 with no restrictions at all. Out of those groups, there are 20 that have no red cards. And the question is, how many groups have at least one red car? So what we're looking at here is kind of a special case. We're looking at this at least one situation. Because whenever you read at least one, it means that you've got a special way of dealing with this. Now on this page, all we're going to do, I'm not going to give you any fancy terminology or anything. We're just going to use our common sense here. So let's look at this one again. There's 103 groups in total. 20 of those groups don't have any red cars in them, but all the other ones must have a red car. In fact, they must have at least one red car, meaning they could have one red car, they could have 2, they could have 3, they could have 4. But the work here is really easy. All I have to do is take all the possible groups that exist, subtract the groups that don't have any red cars in them, and I see that there'd be 103 groups of cars that would have a red in them. Now, don't get too worried about this at least one red. It just means they've got some number of red cars in them. Could be 1, could be 2, could be 3. We don't even know in this question how many are in the group. So just really trying to keep it simple, just this common sense piece. Okay, and in this one, here's the total number of 5-card hands that you can make with the deck of cards. Here's how many of those hands have no aces. Well, all the other hands must have at least one ace. So if I took the total number of hands that have no restrictions at all, and I subtracted the ones that have no aces in them, what I would be left with is the number of hands that do have aces in them. And hopefully I haven't hit any buttons wrong. And you don't have to write any of this stuff down. I just want you to just be thinking about this. This should make sense to us by the time we're done. There are 28 different student clubs at a school. 15 of those clubs have no grade 9 members. Well, all the other clubs must have at least one grade 9 member. So take the total number of clubs, subtract the 15 clubs that don't have grade 9 members, and what you're left with is there'd be 13 clubs that do have a grade 9 member. One or more, we don't know. We know there's at least one grade 9 member. The card game Spritz requires a special deck of cards. With this deck, it is possible to make 2,500 groups of 3 cards in total. So that's as many as you could possibly make, no restrictions at all. 2,500 groups of 3. In these 2,500 groups, there are 800 groups that have no stars. So if I was to take that 2,500, the total number of groups, subtract the ones that have no stars, then that means that I would have 1,700 hands that do have at least one star. All right, so little common sense there, and now let's get back into it. So on page 103, consider a standard deck of 52 cards. So back on the cards again. How many different 5-card hands can be formed containing? So I really want you to watch for this because we're treating it like a special question. When you read at least one, as soon as you read that, remember, oh yeah, that's that common sense thing. That's where we're going to use subtraction. So as soon as you see that, you want to think about using subtraction. Now here's where I'll sort of show you what your little plan would be. So whenever I read at least one, here's what I'm doing. I'm going to take the total number of combinations. So no restrictions at all. And I'm going to subtract. In math, we call it the complement. Now, we've seen that word before. We've talked about it kind of like it's the opposite, or in set theory, we said complement is kind of like putting the word not in front of it. So let's see what it would look like in this particular question. So the way that I have it here in the blue box is the way that we would do it for any question that says at least one. This is going to be our plan. So in this particular question, let's read it again. How many different 5-card hands can be formed containing at least one club? So the complement for at least one club is no clubs. So if we were looking for, let's say, at least one blue candy, the complement would be no blue candies. If we were looking for at least one adult, the complement would be no adults. All right, so let's see how this one's going to play out. So we want to find the total. So how many 5-card hands without any restrictions at all? That would be 52 cards. Choose 5. So that's going to give us our total number of 5-card hands, every possible one that could be made. And we're going to subtract the no clubs. All right, so for cards, let's look at how many of these cards. Look at your whole deck here. How many of these cards? I've already forgotten. How many of these cards are not clubs? So it's like we're saying, get rid of these clubs. And we'd be looking at all of these ones that are not clubs. So 52 in the deck, subtract the 13 clubs, there are 39 cards that are not clubs. So if we want to figure out how many 5-card hands have no clubs, we say, well, there are 39 cards available that are not clubs. And we're going to choose 5. And it comes out to be 2,023,203. Now our workbook only gives us this one example. So I've just made up another example for you. You don't have this one in your book, but I want you just to hit pause and just give this one a try. Look back at the one we just did. See if you can make sense of this one. And remember, we want this to feel like it is common sense. So consider a standard deck of 52 cards. How many different 5-card hands, so we're making groups of 5 or combinations of 5, can be formed containing at least one king? So at least one. Those are the words that tell me use the complement. Now the complement of at least one king would be no kings. So my plan here is to take the total number of 5-card hands that without any restrictions, how many could be made, and then I'm going to subtract all the ones that have no kings, and the ones that are left would have a king in them. So I'm taking all the ones that are possible, remove or subtract all of the groups that have no kings, and what you're left with are the groups that have kings, or have at least one king, to be specific. So let's go our total 52 cards, choose 5. So that's going to give us every possible combination of 5 with no restrictions. Now I'm going to subtract out the ones that have no kings. So there are 48 non-kings available. We want to choose 5. And I end up with 886,656 5-card hands that have at least one king. So really watch for that at least one. And then probably the first 1 or 2 times you see it, you'll need to look back at your notes, but hopefully it will kind of settle in with you. All right, and we are ready for our practice work. So everybody should be practicing these 5 questions on page 104. And that's all we're doing in lesson 6. I know that there are more examples and more questions, but for us, for this year, that's it. That's the important part from lesson 6. Good luck on your work, you guys, and don't forget to check your answers using my attached solutions.